and welcome to our Thesis 1 final presentation. I'm Marwan Abbas. I'm with my colleagues Ahmed Rahman, Mohamed L Atroush, Nouran A Flaifel, and Zeyad A Zaki. Our supervisors are Dr. Mohamed Shalan and Dr. Tamer ElBatt. Today's agenda, we're going to start by introducing our topic, introducing the system hardware and system architecture. Then we're going to talk about our system uses and features. And then we're going to show you our user interface and then discuss the non-functional requirements, the system challenges that we faced, and our deployment plan. Then we're going to conclude by our future timeline. Until January 2019, Egypt's elderly population had reached 6.5 million, which is about 6.5%, and it is expected to increase to up to 11% by 2026. And with our fast-paced life, we cannot dedicate enough time to spend with them, and they prefer their freedom and independence over being kept at a senior care center or having a caregiver living with them full-time. And according to the World Health Organization, approximately 646,000 individuals die from falls globally, making falls the second highest cause of accidental or unintentional death worldwide. This problem is specific for adults older than 65 years of age, who suffered from the greatest numbers of fatal falls. And now Mohamed L Atroush is going to talk more about the applications that try to tackle this problem.
Okay. There exist some similar applications that are actually on the market for the elderly care segment. For example, iHealth, Canary Care, and Quido. However, they all require a lot of hardware devices to be set up. Also, Birdie is a health communication software where patients can communicate easily to their doctors using that platform. And finally, Medical Guardian is a fall detection alert system. However, none of these platforms work here in Egypt. Okay. So ECARE is a mobile application that connects to the elderly's smartwatch to monitor their health and well-being. Our system mainly focuses on fall detection and indoor localization. Not only that, our application aims to make the communication between the elderly and their caregivers easier by having a communication channel where users can, where the elderly can chat and send their reports and medical updates by their doctors. Also, our app will be generating real-time health data and reports. Now for the system hardware, we will be using a smartphone, either iOS or Android, the FitBit smartwatch, and finally the BLE beacon, which will be used for the indoor positioning system. Okay, for the architecture, the smartwatch will be connected to the BLE beacons in order to calculate the distance and detect in which room is the user currently in. Smartphone will be connected to our web API to collect real-time data of the sensor's readings that was sent through a companion application, which is developed on the smartwatch. And now, Marwan will talk more about the system users.
Our system users are classified into two users, patients and caregivers. The patients are the elderly who the system is aimed to support. And they have to have a smartwatch, in this case, a Fitbit, and they have to have a Fitbit account. The caregiver, on the other hand, can include personal doctors, caregivers, and family members. And they all share the same functionality, as they all use the system in the same way to communicate with the patients and view their health data. And here you can see our system use case diagram, which shows you how the users communicate together. And you can see more about the use case diagram in our SRS. But here we have the patient and the caregiver both doing the same functionalities like signing up for ECARE using Facebook, Google, or their personal email, and they can communicate together using posts on the patient's wall like text or documents. And then we here see the first system feature, which is the health tracking. In our health tracking, we can show data like the heart rate, skin temperature, step count, and calorie burn, and the sleeping patterns. And using these sensor readings from the Fitbit, we can then generate reports for both users. And then we can start doing some emergency algorithms using cutoff thresholds on these readings to notify the patients and the caregiver. And due to that, we didn't have any knowledge about mobile application development. We started taking a crash course in Flutter. And after finishing that crash course, we developed the app that you can see on the right, which basically gathers information about the average resting heart rate from the Fitbit web API and displays it here. And that's the data that we're going to start doing our report generation on. And then next, Zeyad is going to talk more about our fall detection algorithm.
Okay, so we started working on developing a deep machine learning model for the fall detection. So the first step was to find the suitable data set to train our model. We decided to go with the sysfall data set because we found that it was the most complete data set and the most commonly used in research in general. They had participants from all ages, and they had the age sector that we specifically wanted to target from 60 to 75 years old, all with different genders, weights, and heights. The data was acquired using 3D accelerometers and a gyroscope, but we will not use the gyroscope, we only use the 3D accelerometer in our training. And it was collected at a frequency 200 Hertz. As you can see here in the video, this is the type of falls that were tested. There were 15 different types of falls and 19 different types of activities of daily living, such as walking, jogging, sleeping, sitting, getting into the car, and all of that in order to establish a difference between when it's a fall and when it's a normal daily life routine. Okay? For data pre-processing, we use the sysfall data to classify it into two classes, background and fall. So all the 19 different types of ADLs are simply have the class label as background, and not all the fall data are classified into fall, because as you can see on the right, these are the accelerometer readings in a fall file. Okay, so the fall is only the part in the blue rectangle. These are only the readings that are described as fall. Okay, and to train the model, all the labeled sysfall sequences were divided into windows of 256 readings, having a stride of 50%. The 156 readings are 1.28 second frame, and as you can see on the right, these are the graphs and accuracies of the different window sizes, and they found out that the 256 or the 1.28 seconds frame yielded to the best accuracy. So whenever a frame had a 10%.
Oh, I'm sorry, I just wanted to acknowledge in some of the video quality might not be very clear, so please, if any slide you cannot see, please let us know at the end that we can show it by sharing our original slides. Sorry about
that. Readings as fall, the whole frame was labeled as fall. Okay, now moving on to the model description. We used a recurrent neural network with two LSTM layers and two fully connected layers, one at the beginning and one at the end. Of course, the end one goes to a softmax to determine the classes. It has two outputs, either fall, all, background, and the dropout layers are used to prevent overfitting. This model was intentionally made simple because it will be deployed on the smartwatch, so it needed not to be too large or too complex to accommodate the watch memory size and all of that. Okay. So while implementing, the data was found to be severely imbalanced. As I mentioned, the background data was much more than the full data because it had all the ADL combined. It yielded to 50 times more of the full data. So we found that we used weighted cross entropy in the implementation to balance the loss function. And these are the equations that we used. Okay, moving on. Here are the confusion matrix or the results of our model. The one on the left was without using weighted loss. As you can see, it did not detect the class 1, which is fall here. It only yielded 9% accuracy. After that, when we used the weighted class, we yielded directly 85% without even tuning the parameters or anything. And after we tuned the parameters, our final model yielded to 94% accuracy of the fall. And now Nouran will continue on that topic.
Okay, so this is our view for implementing our fall detection system. Of course, as we mentioned, the elderly people will be wearing their watches. So the watch will have the embedded accelerometer sensor, as Zeyad mentioned earlier, that will be detected, that will be used to detect the falls. So immediately as the fall happens, the watch detects it and displays this message. So either the user decides or the patient decides that he needs help. So this message is displayed for the caregiver, or he decides to ignore if the fall wasn't very severe, or this was a false detection. And of course, if this message stayed unresponsive for 30 seconds, this means that the elderly people may be unconscious. Therefore, this message is automatically sent. Moving on, we've been exploring with the FitBit Studio, which is the development studio for the Fitbit watch. We've been exploring with it to be able to gather raw sensor readings. And as you can see, we've developed this application that simply shows the sensor readings, and we'll be using these accelerometer readings to use it with our model to detect the faults. And now, our future plan for the fall detection implementation, we'll be deploying our model on the smartwatch. Our deep learning model, most probably we'll be using the RNN as Zeyad mentioned. We'll be improving this model based on the frequency of the readings gathered from the smartwatch. If we're lucky enough, we'll be able to gather them at 200 hertz frequency as we trained our model. So we'll be able to use our window size of 256 to be able to catch the fall in the time frame 1.28 seconds. If not, we'll be tuning our model and improving it to match the frequency gathered, to match the frequency that we use to gather the data. So of course, the model that Zeyad mentioned will be a very solid starting point for our implementation next semester. And we just need to add some small improvements to be able to match our purpose. Moving on, Mohamed will be talking about the indoor positioning system.
Okay, for the system features indoor positioning system. According to our research, the most efficient way to implement the IPS system that suits our project is by using BLE beacons. However, if we're only looking for accuracy, then our choice would have been RFID. Signal strength is an issue with the RFID. Also, RFID are more expensive than BLE beacons. BLE beacons actually costs about $10 to $25, and they're much easier to install in any home and use. Okay. So in order to use our system, you need a minimum of 4 BLE beacons. They are going to be placed in the most frequently used rooms, the bedroom, bathroom, kitchen, and living room. In order to differentiate between them, every beacon will have a separate IP address, so we'll actually know which one is installed in which room. So the BLE beacon are used to detect, will be communicating with a smartwatch in order to detect which room or which hardware device is the smartwatch currently close to. So by getting that information, it's much easier to estimate the current location of the elderly. Okay, so for the well-being tracking, it's one of our major features. The daily routine irregularity detection. We divided this feature into 3 main stages. Firstly, the elderly will have to type in their daily routine manually. Secondly, the system will start gathering the data from using the indoor positioning system, as well as the entered data. The final stage is that the system will discard the manually entered data, and it will be fully depending on the gathered data through the external hardware. And now, after presenting the system features, we will now be showing a small demo for the system's user interface.
User interface, of course, the user has to sign up. If he has to sign up as a caregiver, he enters all his data, and now he has his main view with all his patients, and he can add more patients from here. He can view their profile and see their data. He can check their location, and he can also generate reports. And here he can see all his interactions with the other people. So now for the signing up as a patient scenario, he enters all his data. He can send an emergency to all his contacts. He can also send a specific emergency to the specific contact, and he can write him something. And here we have some predefined buttons to make it easier instead of texting. And here he can also view his own profile and view all the sent messages. That's it for our user interface. So then we have our activity diagrams that are included in the SRS document. So these are just a sample to present. Let's quickly go over the generating a heart rate report scenario. First, of course, the user opens an application. He either logs in or creates an account. He adds his ECARE friend, and then he searches for the patient and adds a patient as an ECARE. And if the patient accepts the request, he views his profile and shows his status, and he clicks on generate report and then clicks on heart rate report, and by then the generated report is downloaded. Moving on, Ahmed will be talking about the non-functional.
Okay, so moving on to non-functional requirements. First is software quality attributes. First of them being the availability. We wish for our system to be running around the clock 24/7 and to be available to our users at all time. Moving on to maintainability. We aim to fix our system as fast as possible utilizing Google Crashlytics, which is a feature in Google Firebase, which we'll be using for our backend. Then moving on to usability. We're aiming to make our user experience as easy as possible for our users who will mostly be elderly, and most of them aren't really that tech savvy, so we'll aim to have as smooth user experience as possible. Moving on to portability. We aim to make our app available on Android and iOS, which are the majority of phones used as OSs. Moving on to security and privacy. Firebase, which will be our backend, as I mentioned, supports GDPR and TCPA, which are legal documents that protect users and companies from service providers from infringing on data privacy on their, which are hosted on their servers. And also there are these certificates, which are ISO 27001, 1718 and SOC 123. Each of them is a certificate which provides different kind of report on different aspects of the system, which also entail many points on how safe the system is for a user and also a business which hosts a service on their platform. Moving on to performance, we wish to make our performance, our latency for our program less than 1 second for most things, but some things like the fall detection and the indoor positioning system will have maybe a higher latency as they are more computationally extensive. Then moving on to the system challenges, our system has many. We faced some challenges, but the main one that we faced during the semester is that our IPS requires the FitBit watch to send our system the IDs of the nearest daily beacon. However, the FitBit doesn't have an API to support that at this time. And we also researched how if the FitBit, if we can make one ourselves on the FitBit or something like that. So we thought up some solutions. Some of them being using discarding the watch entirely and using the mobile, the smartphone itself for the localization feature. And another one was exploring if we could create our own API and to extract the data from the watch. And the third one being finding alternative watches which already have the built-in BLA API that we could use for our system. And moving on to the system deployment, this is not really final, and we're still in progress. Still haven't made a final decision about it, but we wish to make our system non-profit, so we would deploy it as a community development-based product. The package would include the smartwatch and the 4 beacons that we have used while developing our system. The package will be sold at the same cost of each of the components individually with no added cost. And then if the user buys it, it would be compatible, as everything would be the same as we use. Moving on, the system will be cross-platform, as we mentioned before, which we already assume that any of our users would have a smartphone because most people nowadays do. And then the system should be able to, we would be able to deploy by the end of the next semester, which is May 2021. And now Marwan will talk about the conclusion and the timeline.
To conclude, so what we've done so far is that we defined and refined the system requirements and architecture. We took a course on how to use Flutter and interact with the web APIs. We learned how to develop face apps on the FitBit Studio. We created the 2 sample applications that utilize the FitBit APIs, the one on the watch and the one on the mobile. We developed a deep machine learning model for fraud detection, which is the RNN one that Zeyad talked about. And we researched the best techniques on developing an indoor positioning system, which is the BLE that we discussed. And we finalized the system requirement specifications and the system design documents. And we'll be submitting them on the deadline date. So for our future timeline, we'll be working in the winter break, and we will be willing to start the development on the ECARE application, the mobile application. And by the start of the spring 2020, we'll be working on the indoor positioning system, on the implementation. And we'll be deploying our fall detection algorithm model on the smartwatch. And by the mid-spring 2021 semester, we'll be fall detection and the IPS features in the mobile application, and we'll be refining them. And by the end of the semester, we'll be wrapping up and finalizing our system and be ready for the deployment. Thank you, and we're ready for your questions.